How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You're driving. The city around you is a maze of unfamiliar streets, a concrete canyon of one-way signs and identical-looking intersections. A decade or two ago, this moment would have been filled with a low-grade, simmering panic. You'd be wrestling with a giant creased map on the passenger seat or trying to decipher hastily scribbled directions on a napkin. There would be arguments, missed turns, the cold dread of being well and truly lost. But not today. Today, you are calm. Your phone is mounted on the dashboard, and on its screen, a tiny blue dot glides smoothly along a brightly colored line. A calm, reassuring voice tells you, in 200 feet, turn right. You turn right. The blue dot turns with you. It is your anchor, your oracle, your unfailing guide. It knows where you are, down to the last few feet, on a planet that is 25,000 miles in circumference. We perform this small miracle dozens of times a day. We summon a car to our exact location. We find the nearest coffee shop. We track our morning run. We share our position with friends so they can find us in a crowded park. It is so seamless, so utterly reliable, that we've stopped seeing it as technology at all. It's just a feature of modern life. Like running water or electricity, the Global Positioning System, GPS, has become an invisible utility that underpins the rhythm of our world. We see the blue dot, and we trust it implicitly. But have you ever really stopped to wonder how it works? Not in a vague, hand-wavy, it talks to satellites sort of way. I mean, how does it actually work? What is the physical reality that allows that little piece of glass and silicon in your hand to pinpoint its own location with such breathtaking accuracy? The common assumption, the one that feels intuitively right, is that our phone must be sending out a signal. A little digital ping that cries out into the void, "Hello, I'm here. Can you tell me where here is?" It feels like a conversation. We ask, and the satellites answer. But what if I told you that's completely wrong? What if your phone never says a word? What if it's a silent, passive observer in a grand cosmic performance that's been playing out above our heads for decades? That is the record scratch moment. The truth of GPS is far more subtle, more elegant, and frankly more mind-bending than most of us imagine. Today, we're going to open the black box. We are going to deconstruct that magical blue dot, break it down to its first principles, and reveal the invisible architecture of clocks, constants, and geometry that holds our world together. Let's first take a moment to appreciate the sheer magic of what we see. That blue dot isn't just a convenience. It has fundamentally rewired society. Think about it. Global logistics chains, the ones that put that banana on your table from halfway across the world, depend on it. Every airplane in the sky uses it to navigate. Farmers use GPS-guided tractors to plow their fields with centimeter-level precision, maximizing crop yields and minimizing waste. Emergency services use it to find people in distress, shaving off critical minutes that can mean the life or death. Even the global financial system relies on it. The timestamps provided by GPS satellites are used to synchronize transactions across continents, preventing fraud and ensuring the stable flow of trillions of dollars. It's a system of such profound importance that its creators were awarded the Queen Elizabeth Prize for Engineering, one of the most prestigious awards in the field. And yet, to us, the end users, it is a frictionless experience. We tap an icon, and the answer appears. It feels like our phone has a supernatural sense of place. It feels like it has a map inside it, and is simply pointing to its own location on that map. This feeling is a triumph of design, but it's a beautiful illusion. It hides the incredible violence of the physics and the breathtaking scale of the engineering required to make it all happen. The truth doesn't involve your phone having a map. It involves your phone solving a puzzle written in the language of light and time. To start opening this box, we need to completely discard our core assumption. Your phone is not a transmitter. It does not shout into space. It listens. Imagine your phone as a person standing in the middle of a vast, dark field. It has no idea where it is. But in the distance, it can hear the tolling of a church bell. Now that church bell isn't listening for you. It's just tolling on the hour every hour for anyone who happens to be within earshot. It's a broadcast. The GPS satellites are just like that church bell. There are currently more than 30 of them orbiting the Earth, a constellation of robotic bell towers in the sky. Each one is constantly, tirelessly, broadcasting a simple message out into the cosmos. And what is that message? It's not a secret code. It's not a complex piece of data. It's just two simple things. This is who I am, and this is the exact time. That's it. Over and over again, 24 hours a day. I am satellite number 12, and the time is precisely 10 hours, 23 minutes, and 15.123456789 seconds. Your phone is simply a receiver, equipped with a very sensitive antenna, listening for these faint whispers from orbit. This is the first, most fundamental principle of GPS. It is a one-way system. The satellites talk, and your phone listens. It's a broadcast system. Just like the radio stations that play your favorite music, you don't have to send a signal to the radio station to hear the song. You just have to tune your receiver to the right frequency. Your phone is doing the exact same thing. It's tuning in to the frequency of the GPS satellites. This simple fact is astonishing. It means that an unlimited number of people can use GPS at the same time without interfering with each other. Whether it's one person in a desert or a billion people in a mega city, the system works exactly the same, because they are all just passive listeners. This is the first crack in the black box. The magic isn't about a conversation. It's about eavesdropping on a cosmic monologue. But that leads to the next, much deeper question. If the satellites are just broadcasting the time, how on earth does that tell your phone where it is? The answer lies in the second fundamental principle, a beautiful piece of physics that connects two seemingly unrelated concepts, time and distance. The signals from those satellites travel through the vacuum of space and our atmosphere at an incredibly predictable speed. The speed of light, it's the universe's ultimate speed limit, a fundamental constant, approximately 300,000 kilometers per second. And because we know this speed so precisely, we can use it to perform a neat little trick. If you know how fast something is traveling, and you know how long it's been traveling, you can figure out how far it has gone. It's the simple formula we all learned in school. Distance equals speed multiplied by time. If you drive your car at 60 miles per hour for 2 hours, you've gone 120 miles. GPS works on this exact principle, just with much, much bigger numbers and much, much smaller slivers of time. Here's how it plays out. The satellite broadcasts its message. The time is now. Your phone receives that message a fraction of a second later. Inside your phone, a small chip compares the timestamp in the satellite's message with the time on its own internal clock when the message arrived. That tiny difference, that delay, is the travel time. It's the t in our equation. Since we know the speed, s, the speed of light, we can multiply them together and find d, the distance to that satellite. So if the signal took, say, 0.067 seconds to arrive, your phone does the math and concludes, okay, I am exactly 20,100 kilometers away from that specific satellite. This is the core secret. The entire multi-billion-dollar GPS network, with all its rockets and ground stations and atomic clocks, is, at its heart, a fantastically elaborate system for measuring distance. It turns a question of, where am I, into a question of, how far am I from a few known points? Now we get to the geometry. Knowing you're 20,100 kilometers away from a single satellite is useful, but it doesn't tell you where you are. It only tells you that you are somewhere on the surface of a gigantic, imaginary sphere with the satellite at its center. You could be in North America, or the middle of the Pacific Ocean or Antarctica. To narrow it down, you need to listen to more than one bell. Your phone's receiver is constantly scanning the sky, and at any given time, it can usually hear at least 4 satellites, and often many more. So, it gets a signal from a second satellite. This one says, I am satellite 25, and I am 22,000 kilometers away from you. Now you have 2 giant spheres. Where do 2 spheres intersect? They intersect to form a perfect circle. You've gone from being anywhere on a huge sphere to being somewhere on a single, vast ring in space. We're getting closer. Then, your phone locks onto a third satellite. It does the same time delay calculation, and figures out, I am 21,500 kilometers away from satellite 18. It now has a third sphere, and when you intersect a third sphere with that circle we just made, you narrow your location down to just 2 possible points. Usually, one of these points is a ridiculous answer. It might be thousands of miles up in space, or moving at 10,000 miles per hour. Your phone's software can easily discard the impossible option, leaving only one possibility left. That point where all 3 spheres intersect is you. That is your latitude and longitude. This process of using distances from known points to find your location is called trilateration. It's the geometric engine at the heart of GPS. 1 satellite gives you a sphere, 2 give you a circle, 3 give you a point. It's a beautiful, elegant, and almost simple solution to an incredibly complex problem. But if you've been listening closely, you might have spotted a flaw in this plan. A massive gaping hole that should cause the entire system to collapse. The whole thing hinges on measuring the travel time of the signal with utterly insane precision. The speed of light is so fast that a tiny error in timing creates a huge error in distance. If your clock is off by just 1,000th of a second, a millisecond, your calculated position would be off by nearly 300 kilometers. You think you're in Boston, but your phone would place you in New York City. To get the meter-level accuracy we expect from GPS, the timing has to be accurate down to just a few nanoseconds, a few billionths of a second. This is where the satellites come in. Each GPS satellite is carrying not just a radio transmitter, but one of the most precise timekeeping devices ever created by humanity, an atomic clock. An atomic clock isn't like the clock on your wall or the quartz watch on your wrist. Those clocks use the regular swing of a pendulum or the vibration of a quartz crystal to keep time. An atomic clock uses something far more fundamental and stable, the vibration of atoms themselves. Specifically, they use the incredibly fast and unbelievably consistent oscillation of a cesium atom when it's excited by microwaves. It is so precise that a modern atomic clock would only lose or gain a single second over hundreds of millions of years. These clocks are the heart of the GPS system. They are the metronomes that provide the stable, unwavering beat against which everything else is measured. They are maintained and synchronized by a network of ground stations around the world, making sure the entire constellation of satellites is ticking in near-perfect unison. So, the satellites have these miraculous clocks. But what about your phone? Does that $500 device in your pocket contain a multi-million-dollar atomic clock? Of course not. Your phone has a cheap, mass-produced quartz clock, the same kind you'd find in any digital watch. It's a fine piece of engineering for everyday life. But in the world of nanoseconds, it's wildly inaccurate. It drifts and errs by comparison. Its timekeeping is millions of times worse than the clocks on the satellites. So, we have a problem. Your phone receives a message saying, "I sent this at time X," but its own clock is wrong. It can't accurately measure the travel time because its own starting point for the measurement is flawed. It's like trying to time a 100-meter dash with a stopwatch that runs at a completely random speed. The whole beautiful system of spheres and intersections falls apart. The magic should fail. And yet it doesn't. And the solution to this problem is, in my opinion, the most brilliant part of the entire system. It's a trick so clever it feels like cheating. The engineers who designed GPS knew that the receivers would have terrible clocks. They couldn't fix the clocks, so they decided to treat the clock's error as just another unknown variable to be solved. Remember how we needed 3 satellites to find our 3-dimensional position. Latitude, longitude, and altitude, or X, Y, and Z in mathematical terms. We had 3 knowns, the satellite positions, and 3 unknowns, our position, so 3 measurements were enough. Now we have a 4th unknown, the precise error or offset of your phone's cheap little clock. Let's call it T. We have 4 unknowns, X, Y, Z, and T, and as anyone who's taken high school algebra knows, if you want to solve for 4 unknowns, you need 4 equations. This is why your phone needs to hear a 4th satellite. That 4th satellite provides the 4th distance measurement. This gives your receiver a 4th equation. It now has a system of 4 equations and 4 unknowns. Your phone's GPS chip doesn't know where you are, and it doesn't know what the correct time is, but it knows the positions of 4 satellites and its own calculated distance to each one, based on its own flawed clock. By processing these 4 signals simultaneously, it can run through the math and find the one and only solution, the single point in space and the single moment in time that satisfies all 4 distance measurements at once. In the process of finding your location, X, Y, and Z, it also calculates its own clock's error, T, and corrects for it. It effectively synchronizes your phone's cheap clock to the atomic clocks in space for free, as a byproduct of finding your location. Think about that for a second. The 4th satellite doesn't just add altitude, it fixes time itself. It allows a handheld device to bootstrap itself into the most precise timekeeping system on the planet. It is an act of pure mathematical elegance, turning the system's greatest weakness, the inaccuracy of our own devices, into the very key that unlocks its precision. This is the final piece of the puzzle. This is how the magic trick is done. Your phone listens for the whispers of at least 4 atomic clocks in the sky. It measures the delay in their signals using its own bad clock, and by noticing the inconsistencies between those 4 signals, it deduces both its own position and the exact error of its clock, solving for space and time in one single brilliant calculation. But the story doesn't quite end there. There's one more layer to this. A detail so profound it feels like it belongs in a science fiction novel. The entire system is a daily planet-wide validation of Albert Einstein's theories of relativity. According to Einstein's theory of special relativity, clocks that are moving very fast tick more slowly than stationary clocks. The GPS satellites are whipping around the Earth at about 14,000 kilometers per hour. This speed causes their atomic clocks to run slightly slower than clocks on the ground, by about 7 microseconds or 7 millionths of a second per day. But that's not all. Einstein's theory of general relativity predicts that gravity warps time. Clocks in a weaker gravitational field tick faster than clocks in a stronger one. The satellites are 20,000 kilometers up, where the Earth's gravity is significantly weaker. This effect causes their clocks to run faster than ground clocks, by about 45 microseconds per day. When you combine the two effects, the net result is that the atomic clocks on the GPS satellites tick faster than clocks on Earth by about 38 microseconds every single day. 38 millionths of a second. It sounds like an insignificant amount, a rounding error. But remember, this is a system built on nanoseconds. If the engineers didn't account for these relativistic effects, the entire GPS system would fail catastrophically. The errors would accumulate, and within a single day, your GPS position would be off by more than 10 kilometers. The blue dot would be useless. So, built into the very mathematics of the GPS system are constant corrections for Einstein's theories. The clocks on the satellites are intentionally engineered to run slightly slower to compensate for the effects of relativity they will experience in orbit. Every time you use your phone to navigate, you are using a practical, everyday device that relies on the fundamental truth that space is curved and time is relative. The ghost of Einstein is, quite literally, in the machine. So let's step back and look at what we've uncovered. We began with the magic of a blue dot on a map, an experience so simple it feels like our phone is just asking for its location. We peeled back the layers and found a reality that is infinitely more fascinating. We discovered a system built not on conversation, but on listening. A one-way broadcast from a constellation of robotic clock towers in space. We learned that the core secret isn't about location, but about time. By measuring the travel time of a signal moving at the universe's ultimate speed limit, we can transform time into distance. From there, we found the first principles, the irreducible truths upon which this entire global utility is built. The first is that the speed of light is a known constant. The second is that three intersecting spheres define a unique point in space. And the third, most elegant principle, is that a fourth sphere can be used not just to find our place, but to fix our broken perception of time itself. We built a system so precise that it must account for the bending of space-time predicted by Einstein, a daily proof that the universe is stranger than our everyday intuition would have us believe. The blue dot isn't magic, it's the solution to a beautiful geometry problem, written in the language of physics, solved in real time by a tiny computer in your hand. Understanding this doesn't diminish the wonder. If anything, it enhances it. To know that inside your phone, a silent symphony is playing out, a harmony of signals from space, each one timed by the vibration of an atom, all of it corrected for the curvature of the cosmos, is to appreciate the true depth of human ingenuity. It teaches us that the most transformative technologies are often built by taking the most fundamental rules of the universe and applying them with breathtaking creativity. The GPS network is a monument to that idea. An invisible, silent, and ever-present machine that works by measuring the echoes of atomic heartbeats from space. It anchors us, not through magic, but through the elegant and inescapable logic of the cosmos itself.
You've been listening to First Principles. Until next time, stay curious.